Welcome everybody today to Sanborn and AppGeo's webinar, Maximizing the Usefulness of Lidar Point Cloud Data. I just want to introduce your presenters today. With you today are Jason Caldwell and Srini Dharmapuri. Jason is VP of Business Development and Sales, and he has 23 years of experience in GIS, remote sensing, and mapping. And I think those of you who know him and those of you who don't will soon see that he's brimming with enthusiasm and stories from that really deep well of experience that he has. Srini is Sanborn's chief scientist, and he has 30 years of experience across the world in remote sensing, photogrammetry, LiDAR, cadastral, mapping, and GIS services, and on and on. And he's one of the most thoughtful people that I have met in the industry. Myself, I'm Tom Harrington. I'm the Chief Marketing Officer here. In the recent past, I was with AppGeo for 20 years and joined Sanborn last year when we were acquired. And one of the things that I've been enjoying for the last 6 months is learning about the rather remarkable history, both the past and present of the company. So today, this is what we're going to be talking about. Very briefly, I'll kick it off, just our journey to LiDAR. We're going to set the table by talking about the standard LiDAR offerings and uses. And then we're going to go deep and wide, talking about the full range of derivative products. Some you may know, some you may not know, and some of the use cases along with them to really enrich the view of how LiDAR can be useful. The Sanborn history is a rich one. For those of you who haven't worked with us yet, we were founded in 1866, one of the original mapping companies that really pioneered the detailed maps of neighborhoods, streets, buildings, infrastructure such as water lines, even down to the level of detail of what buildings were constructed of. And all of this was originally dedicated to looking into and supporting the fire insurance industry. And over the next 100 years, those maps really became the gold standard for detailed city maps. But Sanborn kept evolving, and you can see from this timeline, started to get into ortho imagery and LiDAR pretty early on in their development. So to get us started, I'm going to turn it over to Jason, and we're just going to roll through this, and I'll see you at the Q&A.
All right, thanks so much, Tom. Appreciate that. So it's a pretty exciting time in terms of LiDAR. I know there's quite a few participants on this call, so there's a lot of interest in LiDAR these days. I'd like to kind of give a little bit of background on where I came from. I started at Sanborn, 23, 24 years ago, being a stereo compiler. And as part of that role within the company, I was tasked with collecting 1,500 points an hour. That was what my quota was. And when we talk about LiDAR today, we're collecting millions upon millions of points a second. So just within my career, there's been this, paradigm shift in terms of how remote sensing data is collected and how it's processed. And that's really why I think so many people are excited about LiDAR. If you're not familiar with LiDAR, real quick overview, it's just the technology is light in the form of a laser beam pulse that we can measure the Earth's surface. The actual technology allows for you to actually observe both ground and non-ground features. So as you can see in the bottom image here, we can capture points off of the ground as well as, low-lying vegetation, higher vegetation, as well as structures themselves. So the technology does a great job of capturing anything that's on the surface of the Earth. And as we roll through the next few slides, we'll talk a little bit about why that's so valuable. So one of the things that we always like to talk about to start with when we talk about any type of remote sensing data, whether it's imagery or LiDAR, is the resolution. And the reason why we talk about this up front is the fact that the resolution will dictate what type of use cases we can use the LiDAR data for. And that's an important aspect to think about as you're looking at your LiDAR programs. And so this slide is just going to kind of walk through 4 different resolution types, starting at what we call the 2 points per square meter, which happens to be the baseline requirement for the USGS QL2 and the 3-depth program. But as we go up in resolution, what you'll see from this image, this is 4 points, the next will be 8 points, and then we'll finally show 16 points. As we get to the higher resolutions, it's very obvious that the features that we can extract and the features that we can see within the data set become more evident. And so this is just a discussion point that you'll see as a theme throughout this presentation, that what you're looking at in terms of density will impact how you can use the data downstream in terms of your business processes. As we talk about LiDAR, one of the exciting parts of what's happened over the last 7 to 10 years is the fact that the USGS has done a great job to take on a program called 3DEP. 3DEP was really the migration from a traditional 30-meter and 10-meter DEM to a LiDAR surface. The image here on the right kind of demonstrates what the difference in quality is between those two products. The left obviously is a 30-meter DEM, and on the right is the exact same area, but with a 1-meter LiDAR derived DEM. Obviously, there's a huge difference in quality, accuracy, and fidelity of the data set. What's incredible about the USGS program is the fact that they are going through and mapping the entire United States. I believe they're well over 80, almost 90% complete right now. So basically, anybody in the lower 48 is going to have access to a great foundational layer that they can use for a lot of different use cases. One of the cool things about this program is that the USGS did do a study, and through that study, what they showed is the cost to collect and process and use the LiDAR. They saw a 5-to-1 return on the investment. And so this is a pretty incredible number. And after Srini talks, I'm going to talk a little bit more at the end of this presentation about how to improve that return on investment by democratizing data and expanding the use cases of the data itself. So just as a real quick review, the USGS, the 3DEP program has some pretty minimum basic deliveries that are provided. This will set the foundation for the rest of the derivative discussion that Srini will present. The bare earth classification is your standard classification. Typically, that's at 2 points per square meter in terms of its density. And then we're delivering both DSMs, DEMs, intensity images. And then we also go through and do what's called hydroflattening by identifying water bodies with break lines and making sure the LiDAR is flat in those areas. And so this is the basis product that is out there. This product is available in the public domain, and it really gives you a foundational layer to kind of work from to start thinking about what else you can do with the data beyond what the primary products have been used for and supported for. The one thing I will mention before I hand it off to Srini is the fact that Sanborn is a prime contractor with the USGS on the GIPSy contract, which is the primary contract where all the 3DEP data is being completed. So not only are we talking about this here, but we've actually collected a lot of the data in support of the USGS and in support of some of our customers. With that said, Srini, I'll let you take off.
Okay, thank you, Jason. So for the presentation, what we have done is we have categorized various products under different topics. So what we are showing here is we group the products under topographic, vegetation, buildings, hydrographic, utilities, and synergistic. I will cover about on the first 5 and leave the synergistic to Jason back again. Primarily, I think, one of the important things that, Jason mentioned earlier is at this time, the core classification of USGS is primarily to classify the LiDAR points, regardless of the density, whether it is a 2 points or 8 points or even a higher. We classify the points as ground and non-ground, and that is where we stop there. But I think the presentation here is, I think we can use the full spectrum of the LiDAR data and extract more information from the current existing LiDAR or any of the future collection. And what we are seeing in this slide is primarily the LiDAR, the LAS file format, which is the industry standard LAS format. As I said earlier, I think the class 1 and class 2 are the only 2 classes that primarily we classify at this time based on the USGS specs. And what I'm trying to cover in this next few minutes or a few slides is primarily, focus more on the other classes, primarily the low vegetation, medium vegetation, high vegetation building. That is one set of classes. On the other side, starting from class 13, which is wire conductor, transmission tower, and class 16. And I think so from 13 to 16 and class 3 to 6, these are all the classes that can be classified. Then in addition to the ground, what we are currently doing, that way we can create many derivative products that will have many use cases. Next slide, please. So this is where I think I said earlier, I think the top left table is what currently we are doing. Primarily, what we are doing is, though there are a few 7 classes are there, but primarily it is class 1 and 2, which means ground, and anything which is not ground, it goes into the non-ground, which is processed but unclassified. That is how it is categorized. But what we are suggesting is, we take the existing data or the new data, add the other classes in the classification schema so that you will have the class 3, 4, 5, and 6 primarily for low vegetation, medium vegetation, high vegetation and building. And class 14 is culverts, which is primarily on the different set of use case, which I will talk subsequently. Or if you want to concentrate only on the vegetation, then, just to focus on 3, 4, 5, which is primarily the vegetation classification. So what you are seeing, the graphics in this slide is primarily ground, and the other rest of them are processed but unclassified. But when you go to the next stage, now everything has been classified. In this graphics, you see the ground, the red indicates the buildings, and the green indicates the vegetation primarily based on the height it has been classified. We go to the next one. So let us go each product at a time. And I want to make sure to the audience here, I think whatever the products we show here is only a small subset. There are many other products can be derived. And if you go through the literature, you will see many more products, derivative products that can be obtained from the LiDAR than what we are showing. So let us take the topographic product. The first 2 is already part of the USGS, so I don't want to spend time. Many people are aware of that. And what I'm going to talk about is the new ones, which are the normalized DSM, digital surface model, nDSM, contours, slope, aspect, Burr, hillshade, highest heat hillshade. So let us talk about few of this in the subsequent slide. So the nDSM is primarily, it represents the height of all the features, whether it's a man-made objects or a natural objects above the ground. So basically, it gives you the height of the feature, not the elevation of the feature. So how you do that is, you after you classify the LiDAR, you create the DEM, you also create the DSM, and then nDSM is created by subtracting the DEM from the DSM, which is how you create the normalized digital surface model. As I said, it provides height of all the man-made as well as natural objects, whether it is trees or buildings, you will get the height of the features. Next one. So this is exactly whatever I talked in the earlier slide is shown in a graphical form. So what you're seeing on the left-hand side is the DSM, and the right-hand side is the DEM. And when you subtract the DEM from the DSM, you get the normalized DSM, and that is what is shown in the bottom of the slide. Next one, please. So the contours, again, people who come from photogrammetric thing, they know that the contours is one of the important product. We have been using it for long. One of the important thing is, by definition, we all know contour connects the points of equal value or equal height. And predominantly, when you create the contours earlier, the contours used to be created using photogrammetric methods. So people used to see a generalized or a smooth contour surface product. But with the LiDAR, what happens is that you get more reflections or more returns. And as a result, the contour derived from the LiDAR will not be as smooth as it is derived from the photogrammetry. And based on the current specification, USGS QL2 LiDAR supports 1 foot contour that can be created as a derivative product using the current QL2 LiDAR data. Next one. So the slope and aspect is another derivative product. Primarily, you can create from the ground points, and we all know the slope is basically the height by distance. Which is, and whereas the aspect is, it is primarily the direction of the slope. And so the aspect primarily is, given in the form of angles, and it shows from 0 to 360 degree, where the 0 is north, 90 is east, 180 is west, and 180 is south, and 270 is west facing. There are various use cases in which the slope and the aspect is, primarily used. I would say there are couple of things. One is the site selection. The other one is the 5G planning, line of sight. And the other thing is nowadays, another important use case is primarily identifying the houses that are suitable for placing the solar panels. That way, not only the house, the orientation of the house, the slope and orientation of the roof is one of the important parameters, but also the surrounding the house, the slope and aspect also is one of the important parameters to study, especially for placing the solar panels on the roof of the building. The graphics you show on this slide, the previous slide, is the left is the slope and the right is the aspect. That's what it is. The left is the slope and the right is the aspect derived from the elevated ground points. Next one, please. So the Hillshade is another product that can be created from the ground points, and primarily it gives you the lighting effect to your elevation. So that way it gives you the elevation variations within the landscape. And it gives you the sun effects, primarily illumination, shading, and shadows, etc. That can be seen with the Hillshade. Of late, I've noticed some of the people who are involved in the elevation derived hydrography or 3D HP use this as one of the product to validate some of the streams, or to make sure that the QC of the product, they use this product as one of the supporting data to validate, or to make sure that all the data that is captured is correct. So that way the Hillshade plays an important role in the QC process. Next one, please. So with that topography, having completed topographical products, we go to the vegetation. This is where I think I said that, in addition to the classification of ground points and unclassified points, this is where we need to go one step further. And then we need to classify the low, medium, and high vegetation. And that is purely classified based on the height. And once that is done, then you can create these derivative products, which are primarily canopy height model, height above the ground, tree canopy cover, 3D vegetation polygons, and vegetation height raster. So let us take few of these products. And before that, I think this is a slide, I think, primarily like earlier when I showed you the ground, building, and vegetation, exactly this is the same thing. But to show you first the raw data, and then when you classify the vegetation based on the height, that is what the product you get. And primarily, it enables you to see the grasses, trees, and shrubs to be separated based on the height. And that is one of the important things that needs to be done before we create any of the vegetation-related products. Next one. So the canopy height model is one of the derivative product. Once you have the classification of vegetation is completed, it maps the tree height as a continuous surface, and also it represents the tree overstory. And again, there are so many use cases for the canopy height model, the CHM. I'm not going to read up everything, but primarily I would say the most important thing is the fourth bullet, which is primarily modeling the forest metrics like tree size, basal area, volume, and all those things. That's one of the important derivative product that assist in terms of calculating the metrics. And the other thing is, of course, the solar energy assessment, the CHM is again used because vegetation can be a source of obstruction. And finally, the line of sight, especially with the 5G planning that has come into play, the line of sight, radio wave propagation modeling, and wireless planning, this product is a very, very useful product. Next one. The height above the ground is primarily the difference between the first return surface as well as the last return surface. So it's primarily you take the surface created from the first return and take the surface created from the last return, and then you find the difference between those two things, and that is what it gives you the height above the ground product. Next one, please. A tree canopy cover is another byproduct or a derivative product. Once you have the vegetation classified, then you can create. It's primarily used for canopy thinning operations, and also in the case of reducing the risk of the wildfire. So this is one of another derivative product that will be very useful in terms of mapping the forested areas as well as targeting the areas where the thinning operation needs to be carried out to avoid the wildfire risk. So next one. So with that, we completed the vegetation. So we go into the buildings, and as we all know, buildings is one of the very important feature to be extracted, whether it is from LiDAR or from the imagery. There are so many products can be created from the buildings, but what we are showing here is building outlines and 3D building models. And as you know, the buildings is one of part of the impervious surface. That means, any of the cities which are involved in the stormwater management planning and other things, they would like to have the information on the impervious area, which means in the total area of the impervious, in the total impervious area, buildings will constitute a significant percentage. So in this, in the case of buildings, again, you go through the building classification. You can create a 2D or a 3D outline or a 3D wireframe. That is what is shown in the graphics here. Predominantly, the buildings have been captured using the photogrammetric techniques, either 2D from orthos or 3D from stereo compilation techniques. With a LiDAR, you can use a semi-automated process around 80 to 90% of accuracy. You can almost format the data so that it can be directly taken to any of the GIS platform, including SRI, or it can be a CAD to a CAD MicroStation or AutoCAD. Also, you can take it. And as I said earlier, buildings is a very major component contributing to the impervious surface. And so any of the stormwater studies, impervious mapping, buildings will be one of the important parameters one of the buildings is one of the important layer that needs to be created for those type of studies. Next one, please. Now we're going to the next one, which is the hydrographic. So what has happened is, can you go to the next slide? So this is something currently we are doing. This is what Jason covered earlier also. With the current QL1 or QL2 LiDAR, what we do is we capture all the lakes and ponds, which are more than 2 acres. And also we capture all the rivers and streams, which are more than 30 meters wide. And using the hydro break lines, we do the make sure that we do the hydro flatten so that the points are all on the same elevation. And also we check the monotonicity in the case of rivers and streams, so that the river flows from a higher elevation to a lower elevation. So what you are seeing, the two graphics, which is well known, people who have been using the LiDAR, they might have seen so many number of times. Primarily what you're seeing on the left-hand side of the graphics is elevation model created, the digital elevation model created without adding the hydro break lines. So that is where you see the zagged thing. Whereas on the right-hand side, when you add the hydro break lines and then you create the elevation model DEM, you can create a very smooth digital elevation model that is being shown on the right-hand side. So this is currently being done. So we are capturing hydro break lines to a certain extent, but what we are proposing or what we are suggesting is that we can go many steps further, and that is one of the program USGS has taken the 3D to the next level, which is 3D HP, which is primarily updating all the water hydro features. Can we go to the next slide? So this is what we are talking about. It is a 3D HP or elevation derived hydrography. Primarily, in addition to capturing a limited number of hydro break lines, currently what we are doing, we can go further up and we can capture more features, lakes, ponds, rivers. Also, we can capture the culverts. That itself is a major exercise. And that way, once we do everything, we can create the flow lines, hydrographic flow lines, feature connectivity, and drainage network, all those things that can be performed once we have the necessary data created from the LiDAR information. So that is one part of the exercise that is being done by USGS under the 3D HP. So there is definitely going to be more information that is going to be extracted from the current LiDAR data. The next one is utilities, and here I want to make sure that I state correctly here. As Jason mentioned about the different points per square meter, which is the fundamental unit for any data collection, LiDAR data collection exercise. So we saw that currently USGS recommends either QL2, which is 2 points per square meter, or 8 points per square meter, which is QL1, and in some cases they go through an hybrid, which is 4 points per square meter. But what utility is a totally different area, but they expect at least 30 plus points per square meter. So their requirement is totally on the higher side. And also it depends on whether it is a corridor-based collection or a wide area collection. Especially if you are involved, if you are going to see the transmission line as well as the distribution line, invariably you will end up in a wide area collection. So we think that, you know, by increasing the point density to the number that the utility companies are looking for, that way you can make the data available to more user community, not necessarily the local or the state agencies, but also the utilities. Also, they can use the data set. So it's the same thing, you know, you collect once and to try to use it for many other areas or many other many use cases or many departments. That is what the purpose here is. So as I said in the LiDAR LAS classes, and this is some of the new classes, you will see the wires, poles, wire guard, conductor, transmission, tower, insulators, etc. These are all specific to the utility industry, especially on the you know, transmission line, the power line type of studies. And what you are seeing, the graphics is primarily, you know, some of the examples of the utility LiDAR data, and you can see on the left-hand side the high density of the data that you can see here. Next one. So vegetation management is one of the important things almost all the utility agencies work on, because any vegetation encroachment will cause a power outage, and that we all know, we rely heavily on the power. And and this is where I think, you know, once you have a higher point density, you can map the areas where the vegetation is encroached, and also the shape of the polygons, how much area it has been encroached. And that way the utility agency can plan for the trimming operations and make sure that there is no power outage in their supply. That is one of the critical things. And again, different utilities handle differently. What I'm showing here, the graphics is 25 feet on both sides of the pole. It can be more or it can be less. It depends on utility to utility. But the important thing is, with a higher point density, you know, what we are trying to tell is, you know, you can meet not only the utility industry, but also the same data either at the same level, which is 30 points, or you can downsample the data to at a reasonable level, let us say 8 points per square meter. That way the other entities also can use the same data. So that is something, you know, you can collect once, but many agencies can use. Jason.
Yeah, thank you, Srini. Appreciate that. So what I'm going to talk about for the rest of this presentation is really how we combine LiDAR data sets with other data sets to provide additional value. It's what we call synergistic data integration. So this discussion will flow into the discussion about data democratization, and the two really kind of align, and so that's why they're combined in this component of the presentation. So when we talk about data integration, really what we're talking about is taking data sets from multiple different collections. It could be different sensors, it can be different time of year that we're actually collecting data and comparing those, all the way up to what we call the Internet of Things, or the IoT type of integration. And so the concept of taking this data and trying to build it into a format that is easier to digest and it answers the questions to the business process that you're trying to answer the questions for quicker and easier is really the concept. And so as we go through the next couple of slides here, we'll talk about a couple of examples of this and get into some deeper dialogue about data democratization. So one of the projects I want to talk about to start with is temporal data sets. I mean, one of the biggest values of the fact that the USGS has completed or is about to complete the first iteration of the 3DEP program is the fact that there's a baseline data set there for all of us to use. This is public domain data. Anybody that wants to get access to it can get access to it. In this example, this is actually pretty close to where our headquarters are at. We're in Colorado Springs. This is actually in Boulder County. It's the Marshall Fire that happened 2 years ago now. It was a unique fire in the fact that it happened in December, which is our winter, obviously. And the fire was essentially put out by a snowstorm. And when we went to do the emergency response, which would usually be done with imagery, we realized that the imagery source, because of the snow cover, was not going to enable us to do our AI damage assessment tool. And so we needed another function. So we decided to choose LiDAR. Again, the image on the left is a LiDAR data set that Sanborn collected in under a contract with the USGS for the 3DEP program. And then the image on the right is the emergency response, where we went and collected data over the Marshall Fire immediately upon the fire being put out so that we can assess the damage. Quickly, just looking at the two images, you can kind of see the difference here. And really the what I would consider the scariness of the image on the right is all the indentions that you're seeing on the ground are houses that were essentially burnt to the foundation. And what you're seeing there is the foundation component that's left. And so as we go to the next slide, we'll kind of walk through this and talk a little bit further about what we did here But the whole idea is we wanted to create a change map to determine the damage assessment. And one of the ways to do that is to take the 3-depth data that was already collected and to do some additional processing on that 3-depth data. That included additional classification for structures and vegetation and things of that nature. So we created that baseline data and normalized that data to the second collect that was completed in 22, right after the actual fire itself. And once we had those two data sets in alignment and normalized, we were able to do the change map, which is actually what you're seeing on the top right there. So it was pretty powerful. Immediately, we could see, you know, from a volume perspective, the type of damage that we were dealing with. But more importantly, we took that data and integrated it with other data sets like parcel and valuation of those parcels that we were able to combine with it. And once we had that combination of data, we brought that into an Esri dashboard to be able to provide better visualization back to the customer. So the bottom right-hand corner is that visualization initially within it. And then the bottom image here actually shows the calculation that we're able to come up with based upon this synergetic product where we combine multiple different vintages of LiDAR data with the parcel data to come up with the damage assessment. It was interesting to see how the remote sensing calculated this versus what the actual outcome was in terms of the calculation that was deemed by the insurance industry. And the two are actually pretty close in alignment, which was really exciting for us to determine that the remote sensing work actually was a great tool to be able to look at early assessment in terms of the damage that was happening here. So obviously the fire itself was not cool. There's a lot of people impacted. They're still in recovery in this area. But to be able to see a use case where the value of LiDAR jumped out immediately was one of the things that really impressed me. And I think most of the customers we talked to about this program, it definitely impresses on them the need not only for thinking about how you would respond to a situation like this, but also having baseline data that you have collected and that is ready to go in case of emergency like this. The other kind of project that we work on typically is what we call a digital twin base map. This is an example of it here. This is an RGB fusion with elevation data that was completed to create this digital twin. I'll just mention real quick, that's the ball arena. That's where the Nuggets just won their Western Championship. So we're super excited about that in Colorado. But regardless, when we kind of think about the geospatial impact of this tool, it really gives you a visualization tool that looks very real. And what's cool about it is you're combining both imagery and LiDAR into a single base map, and you can also overlay additional information. So in this example, we're showing overlays of street and transportation networks, as well as parcel data. One of the customers we work with actually overlaid a tree canopy type of product where they are actually counting the amount of trees within the data set itself. So the tool really gives the power of visualization as well as feature extraction within a 3D environment by combining all of the assets together into one tool. The other one that's pretty exciting that we've been working with is vegetation canopy cover. This allows for biomass indexing as well as other types of extraction of data. This is the combination of LiDAR data with imagery to be able to pull this information out. Again, this type of product has been used for many different use cases. For the past 20 years, Sanborn has worked in and around this type of product to provide support for understanding, you know, the infrastructure in terms of vegetation and what that canopy does to lower cost for the community associated with heat islands and things of that nature. The other thing that we've actually seen this product used for is within the assessment space. We have a specific customer that has used the tree canopy as a component of the valuation. One of those has to do with just the view shed and the shadow that it provides, but the other one has to do with the actual potential value of that property from a commercial hunting perspective. And so there's a whole bunch of different use cases that are surrounding this tree canopy. The other thing I will mention here about this tree canopy project or projects is the fact that the USDA and the U.S. Forest Service have over $1 billion of grant funding available for communities to access to do this exact type of project. And so this is a unique, you know, type of program where you can actually use that grant funding to fly new LiDAR, which typically would be leaf on, which would be possibly a little bit different than the leaf off work that would be collected for the USGS. and combining that with the imagery to be able to provide not only the vegetation mapping, but also a great source of geospatial data for doing other things with. So if you have any questions about that grant program, please reach out to your Sanborn rep. We'd definitely like to talk to you about it and how to work that program in association with the USDA, as well as thinking about how that allows for new data acquisition. The other one that's definitely at the top of everybody's mind right now is how do we get elevation data for under the surface of the water. So primarily the 3DEP program has looked at the topographic components that are outside of the water bodies, and filling the gaps in terms of the water bodies is kind of the next step. And so there's a lot of different capabilities out there from airborne perspective, including Topo Bathy systems. But the one thing that we've identified in terms of our production and pilot testing with these different systems is that the airborne Bathy systems that are penetrating the water can only be used to a certain depth, and they can only be used in a certain type of water in terms of its clarity. And so you definitely have to start thinking about other types of sensors and other types of platforms for collecting data within these water bodies. And so a marine-based type of solution that is using sonar is what makes a lot of sense. In this example, and on this image that you see here on the right, we have this red boundary, and then we have the green boundary, as well as the actual borders that are land and on the shore. And so the thought process in terms of how we approach projects like this and how we integrate this data is that, yeah, you can collect Bathy topo for a portion of that water body up to a certain amount of depth and a certain amount of clarity. And then beyond that, you need to start thinking about other sensors. In this case, we've identified within the green polygon that these are areas that the boat would have access to based upon the depth. And so the ability to use a sonar would provide a significant capability in terms of filling in that gap for the water body itself. But we still would have that gap between the red and the green boundary. And that's where we start seeing some smaller unmanned marine vehicles being used with sonar. Z-Boat comes to mind. It's a system that Sanborn owns that can kind of fill that gap. And so in this case, a proposal may include the ability to say, hey, we'll fly airborne data, we'll mix that with a marine larger boat sonar system, and then come in and fill those gaps in with a smaller unmanned boat system to be able to fulfill the requirements of the Bathy topo. So it's a good example of combining multiple platforms and multiple sensor technologies to get the final end result that you're looking for in terms of the data. IoT integration. So this one is huge. I mean, I'm really, really excited about the Internet of Things and what that potentially provides. We actually are showing 3 different images here that are different types of programs. The bottom left one here is a program that the AppGeo division has been working on, where they've developed an app in concert with the county in Texas to identify potential rainfall and how that is going to impact flooding across transportation networks. So it gives a early discovery associated with that. They wouldn't have been able to do this type of app if they didn't have strong base data that actually demonstrates where the water is going to flow when the event happens. The bottom right image is another example of something that's really cool. And in my perspective, Sanborn actually does a lot of work within the autonomous vehicle space. We build what we call HD maps for that space. And really, that's the first step into this connected car capability, where you're going to have the ability for cars and emergency vehicles and traffic signals and even more information being connected together to allow for better efficiency and better safety associated with our transportation network. The one on the top right is an interesting one. This is obviously just a weather map, but this has to do with the project that we did for our client, which was the state of Arkansas. State of Arkansas is pretty progressive in terms of their remote sensing programs and GIS overall. And so they have a strong LiDAR data set. They have strong floodplain maps already created from that. And they also have capabilities of integrating with IoT, which in this case are stream gauges. In this example, you can see that dark purple and blue and white segment, which was a unique storm that dropped a ton of water within that Arkansas River watershed that ended up essentially the sensors themselves were letting the state know that there was going to be a flood event 2 days ahead of time. And so the state actually contracted with Sanborn to support them in a situational awareness perspective to be able to have both aircraft available as well as data processing available to give them imagery back based upon the input that they had received about this flooding event. So it's pretty cool to know 2 days ahead of time that you're going to be flooding. Not everybody has that opportunity to have both sensors as well as the sophistication of the systems at an event that is upstream that far to be able to do that. But in this case, it was unique and very cool. It also ended up saving lives and saving a lot of property as people were able to prepare for it. So there was a lot of agricultural areas in this region, and so they were able to take the steps necessarily to essentially remove livestock and do other things of that nature. So pretty cool use case when it comes to saying, hey, we use LiDAR as a base foundational data set to enable us to integrate with these stream gauges to now know when we were going to have these events and when these crests were going to happen. And so a project that I worked on specifically, so it's one that's dear to my heart. So, it's great to say, hey, we're moving from, static maps that were built, 50 years ago, 40 years ago in terms of the USGS dam. We're going to integrate that into the Internet of Things, and we're just going to get more and more data, but that really does impact this user community, right? And so, there's, so to speak, a tsunami of data coming, right? First of all, the 3Dep's coming, but we've already seen from a lot of our clients the idea of, hey, we love what we're seeing here, but we think the use case is even stronger if we move up to a QL1 or 8 points per square meter, or even, something that's beyond that, up to a 20 or 30 points per square meter. And so this is just an example of kind of the data tsunami based upon the original USGS NED data set versus the USGS Quality 2 data set versus Quality 1. And this is only for an individual state, which in this case was calculated based on California. And so this is a real challenge for a lot of end users. So trying to figure out, how am I not only going to be able to ingest all this data and use this data, but integrate it while I'm trying to deal with the tsunami of data that's coming in? And so that's a challenge that we're all going to be faced with. And this obviously is the crosswalk from the derivative discussion into this data to democratization discussion. So there is significant challenge, right? Data storage and discovery is a big one that we've seen customers challenged with. And then visualization and analysis is the second component to that. How do we make it easier for our end users to be able to use the data for what they need? What I would say is that this term democratization of data has been used quite a bit in the industry. But in our philosophy and the perspective that we present to our customers is it's not just about making that data available. There's two other components associated with what we need to achieve to be able to be successful in democratizing this data. The first one has to do with educating, right? We want to make sure people trust the data and understand what the data can be used for. There's nothing worse than someone using the data for something it shouldn't be used for, first of all, or not trusting the data and not wanting to use the data at all. So that education is part of this discussion. And then the other one is this pink box here, the self-service analytical tools, right? There's a lot of the user communities, when we think about what they want to do with this data, is there ways to empower them to use the data where they don't have to be high-end scientists or sophisticated engineers or GIS analysts to be able to use the data. So really trying to come up with a concept to broaden the user community with this data is what we're presenting here as part of the democratization challenges. So the top graph here really identifies what we've kind of looked at as three different types of user communities. You have the LiDAR experts, the scientists, the programmers. They can do all kinds of stuff in R. They can do all kinds of cool things, but that community is relatively small. So making sure that we empower them with the raw data that enables them to do what they want to do is important. But the ROI back on that can be limited because that community is smaller. As we go to the blue box here, this is the GIS community, the data scientists and the spatial analysts, the people that know spatial data, and that's what they're rooted in terms of what they do on a daily basis. So that community is quite a bit larger. They know how to work with Esri. They know how to work with other software packages. And they're very strong analysts that can do a lot with the data. So for that user community, just making sure that the web services and that the data is available to them to be able to work with it is important. This pink box, or I say box, but oval, is where we see a significant potential in terms of ROI return. This is where the decision makers, the planners, the engineers, the people that are the non-geospatial focused people, but want to use the LiDAR data to answer specific questions. And so in this case, what we're really trying to achieve is providing them with tools like decision support systems and other types of tools that answer their question specifically, rather than just being focused on the data itself. And I always like looking at Dilbert. They always give out cool graphs. I put this at the bottom here just to get us a little laugh. But your user requirements include 400 features. Do you realize that no human could be able to use a product with that level of complexity? Good point. I better add easy to use to the list, right? And so it's kind of a joke. Yeah, but the 401 is easy to use, but the easy to use point is very important as it pertains to the pink oval here, right? If we can get information in the hands of these people to be able to make the decisions that they want to make by using the fundamental basis of the remote sensing data, then we're going to be much stronger as a community in terms of their interest and support. And the ROI is just that much greater. So to that end, I wanted to kind of demonstrate a couple of examples of tools that we've seen out there that provide this capability to end users. And so Sanborn has two tools. One is called Giza and the other one is called Sanborn Geodata Explorer. Both of these tools really allow for our end users to be able to easily access the data that they have. It can be both raster and vector type of data sets, as well as LiDAR data. This type of tool really provides cloud storage, it provides credentialing, it provides a level of cataloging, and then also has some level of analytics and curation associated with it. And so this enables end users to be able to say, hey, I know where to go get access to the tool. I know the metadata that's behind it. I know the services that would support what I need. And that's great. Now that they have access to that data, they're using the data, that increases the ROI overall. But then back for the administrators, we also have tools that support really viewer user history, location, where is the data being used the most? How is it being used? All this information empowers the larger thought process of education, as well as the thought process of how to look at a program and understand its value and look at the repeatability of that program as you move forward. So with that, I think we'll end with a couple conclusions here. The big one I would say is, LiDAR is a great tool. I mean, to understand all the different unique, derivative products that have been presented by Srini has been amazing. Thinking about how you integrate that data into other types of data to support additional business processes is a huge advantage. It can be used, across government and commercial use cases. It's basically been captured for the entire United States, so the baseline data set is already there for you to use. It's public domain data. What I would tell you is that data not only is public domain, but what Srini was talking about earlier is possibly doing additional classifications. The raw data in the LAS format is available for you. So if you need to take it to the next level, you can do that yourself, or you can work with a vendor like Sanborn to be able to do that additional classification. The idea of collecting it once and using many times is very important, right? And so the thought process that Srini was talking about in terms of an electrical utility entity and how that electrical utility entity may have a different specification requirement versus a different government group, understanding all those uses and understanding what you need in terms of the densities, the accuracies, and the seasonal requirements are very important aspect of trying to do it one time and use it many times. If you create multiple derivatives, that's going to empower a larger user base. And as I mentioned already, the synergetic data integration ends up being something that even evolves farther. Plan for easy to access and easy to utilize tools to support their larger user base. This is huge, right? This gets back to the Geodata Explorer and the thought process of not just saying, hey, the data is available, but making it super simple and easy for the user community to get access and use the data. So overall, what I would mention also is, thinking about as you're developing your baseline requirements and your derivatives and your dissemination solutions, working with a vendor like Sanborn to understand the impact of different decisions that you might be making. That might be budget impact, that might be volume of data impact, that might be how long it takes to turn the data around. There's a lot of different things to think about when it comes to LiDAR data programs. It's important to kind of have a strategic plan and understanding what the end users are going to want to do with the data, right? Understanding that, possibly, running through a needs assessment, understanding what the user community focuses on will drive that. Obviously, budgets come into play there as well. So there's a lot that can go on there in terms of, what decisions you need to make associated with the specifications and the requirements to make sure that you support the broader, user community. However, there's a balance, right? I mean, that Dilbert cartoon kind of illustrated it, right? You have 400 different use cases, but are you going to be able to support all of those? And so it's that trade-off on the ROI associated with, you know, the costs that are associated with it and what you're going to get back out of that requirement or specification. So definitely working with Sanborn to figure that part out is a potential.
So we do have a couple questions coming in. Let's get right to them in our closing 5 minutes. What does 80 to 90% accuracy for roof building CAD models mean? The industry standard is greater than 97% for all roof facets.
Say 80 to 90%, that's a semi-automated without any manual intervention. So you just write a macro with a certain parameters and, you know, train them on macro and then run it on. Definitely you are going to get 80 to 90% of the buildings, they are right. Or when I say they are right, means geometry wise, they will sit exactly on the input data. But that is not the end. As you said, 97% or even more. And I think, you know, you need to take to the next stage where you have to go through manually, clean up certain things, make sure that, you know, everything is in the right place, and, you know, some of the buildings are not missed. That also can happen. So we have to make sure of, you know, basically every building is accounted for, and every building geometry wise, they sit exactly over their input data. So that is the second stage of process that is done. So the 80 to 90 is primarily just running a macro and getting a result.
Right. And I'd add to that there's different use cases, right? So we do have customers that have use cases that exceed that 98, 99 percentile, which we deliver to all the time. However, we have other customers that don't have that same use case. So they're interested in a more automated approach that would be a lower cost approach that still gets them a high quality product. And so this actually drives back to your original question there, Tom, a minute ago about, you know, what are my needs and what do we need to actually achieve with these derivative products for the specific customer.
Thank you. Alec has a question. What sort of data structure standards exist for LiDAR derived object classes, from surface models to vegetation models to building models and on up? What's a good source of information about these sorts of data structure standards? NIST, maybe?
Well, for the buildings, you know, the buildings have had, you know, for 3D buildings, there's, I think it's OpenGL that has there is a standard out there that we've looked at as kind of a template to actually show the different quality levels of geometry. That I don't think was originally written specifically for LiDAR, but it could be used as a foundation for that. Obviously, USGS has a very strong specification document associated with the deliveries that are required for their programs. That includes DEMs and DSMs and other vegetation models. But then when you take it to that next step, in terms of, you know, different vegetation models, you know, I think there's still room for defining that, but Srini, maybe you would be able to provide an additional input there.
You're right. I think the City GML is the format that
correct. City GML. Thank you.
Open Geospatial Standards came with that, and I think, you know, that talks about the different levels, the level LOD 0 to LOD 4, the level of detail, and also, you know, what sort of information that will get into that. So that is one thing. But to answer the question, I think, you know, we can. There are certain standards out there, like the City GML is one thing, but, you know, it depends on product to product, and also what sort of software you are using in now. So ultimately, whatever the product we create, that should go and sit inside your software. You know, we have to be able to ingest the software into your thing. So to that extent, I think, you know, there is a lot of flexibilities there. We can create in different formats and provide the data that can be easily used by the end user. So that's a possibility.
Thank you. More questions coming in. Austin has a question. Could you provide a little detail on LAS data sets, how they're classified for different feature types? For example, how are trees versus light poles differentiated?
That's a great question. So there's algorithms that are built that we use that are automated algorithms that get us to a certain percentile, and then we have to go in and do some cleanup for that. Both ASPRS and USGS have adopted a confusion matrix that allow for a certain percentage of accuracy associated with that classification that we adhere to. What I would mention is that trees do look different than light poles in the fact that there's typically a canopy or a larger structure associated with that tree. And so there is some things that you can use in terms of object orientation and training to make sure that you're segmenting it properly. You know, from my perspective, one thing to recognize and understand is the way that LiDAR works, the individual light pulse has the ability to return multiple different pulses off of that. And so when you think about a tree is what I call a soft return, you'll get a return off the top of the tree, but then you'll get filtered returns throughout that tree, whereas a light pole would not have that same look. And so there's a lot of things you can look at associated with the parameter of an individual light pulse that would aid in differentiating it. Srini?
The second thing is that, you know, there is no single macro that will work across the country or across the thing. So each and every project will call for fine tuning the parameters. In the case of vegetation, height is one of the important parameter. And then, you know, you run on a small area, make sure that the macro works, and then you apply on the full area. That's a step one. And obviously the next step is, you know, the visual lookup and cleaning up the data set to make sure that everything is in the right place. So that is how it is done. But at the same time, you know, this is totally different from the current discussion topic. A lot of people are talking about the machine learning or the deep learning type of thing. So that will be an interesting thing to see in future how it is going to come out.
So I'm hearing, and this is a little bit of a side topic to what we talked about today, but it's that deeper question of working with a partner that has both the collection systems, the automation systems, but also, you know, the kind of the manpower to do that QA/QC, to do that second level or that higher level of confidence data development. And as you said, Srini, we're on the path to automating more and more of those steps, but it's a lot of different pieces that have to come together to make the data at that high level. Looks like the final question here, and we'll stay on to answer it. Are there different use cases for height above ground products versus nDSM? Great question.
It was an interesting question because we talked about this yesterday. Actually, we were preparing for this. So I'll just make a comment that height above ground versus nDSM is obviously, it's very similar product, but one is calculating the height above ground where the other one is calculating the distance between the two. With that said, Srini, I'll hand it off to you to see if you can think of any differences in use cases there.
I mean, as I said, yeah, I think, you know, the use cases are plenty, and especially on the, you know, on the forestry side and, you know, vegetation side, definitely. Maybe I think, you know, I can put some information and I can send through an email to that person on the use cases for.
I mean, yeah, the one thing I will say, nDSM, especially if you're talking about 2 vintages of data, is very powerful tool because that's really showing change. If you're looking at an nDSM within an individual LiDAR data set, then that potentially would have a different use case. But I like that idea, Srini, following up with Michael on that additional detail.
Yeah, and I'd like to just underline that, you know, we're here to answer questions. It's part of our job. That may lead to a discussion that goes deep down into a use case or something you're trying to do, but you know, this is the work that we do every day. We love to talk about it, and obviously we're full of stories. Got another question from Alec, drilling down a bit. From a wildfire risk analysis perspective, being able to pull out tree canopy height and density and directly underlying grass height and density would be very helpful. Can LiDAR post-processing see this spatial structure?
Yeah, absolutely it can. It's going to be somewhat dependent on the seasonal acquisition, right? I mean, dependent on what the canopy is, if it has a leaf off condition versus not, then obviously you'd likely like to see that leaf on if you're going to do a LiDAR collection that's specific for vegetational analysis. The other thing I'll mention is typically, like if you think about places in the Pacific Northwest and in Northern California where you might have a large canopy hanging over the top of grass height, having an increased density in terms of the data collection is very valuable. And also using a sensor that has multiple returns in terms of what's being returned from the ground is very valuable. But yes, I mean, this is actually part of what we have to do on a daily basis is to classify the canopy as well as classifying the height of the understory itself. So specific, you know, we've done that quite often specifically. And so if that's what is needed, that's great. We actually have had discussions with a few clients where they're interested in combining both the airborne data with some ground-based data to understand that structure impact even further. And so this gets back to kind of the synergistic discussion in terms of combining different data sets for the power of the decision support that you're looking for, in this case, wildfire.
Really appreciate your joining us today. Have a great day.